Hello again, this is Timothy Baldridge, and this is part 3 of Let's Write a JIT. Now today I want to talk a little bit about optimizers before launching into an entire new section of this series. And this may actually be the last in the series for now. This will show we'll show some things today about how meta-interpreting helps writing a tracing JIT. But at this point, I've pretty much written all the code on this project that I plan to. I've explored it enough to kind of get comfortable with some of the concepts, and it's just a matter of debugging and extending the code at this point. And I don't know that I have a whole lot of interest in continuing. But this should at least clear up some of the dark areas when we talk about tracing JITs and specifically how they're done in PyPy, and allow us to and allow some people to use these videos to get a basic understanding of the technology involved. All right, so today we're going to talk about, real quick, we're going to talk about optimization. So in our last talk, we stopped here with this trace. We've generated this trace for this extremely simple program. And now we want to optimize it. We can see here that if we're guarding that x is 5, then we can fold all these other instructions. So what we do is write a simple partial evaluator that we're calling optimize here. Now what differs from other partial evaluators is the one we wrote before has to deal with branches. So it's going to other blocks and folding in blocks and jumping around the different blocks. And we don't have to worry about any of that. We're only going to optimize a single trace. So op and our two op clauses here look exactly like they did before. And we have extra clauses for guard, true, false, and value. Now, if there's already a guard in place for each one of these, if the value we're guarding is a constant for whatever reason, then we're just going to remove the guard completely. And we see that with each of these. But if it's not a constant, then we need to leave the guard in place. But we're going to associate into our guard the partial environment. And we'll see why we need that in just a little bit. And when we're all done, we're going to do this thing called generate assignments. Now the reason we're doing this is because at the end of our loop, we want to make sure that we haven't optimized away too many variables. If you remember, our environment when our interpreter is running is a hash map of variables to values. This means that if we run this trace and we've optimized out whole sets of variables, the environment may not have enough data in it for the rest of the program to execute properly. We might have optimized something that the trace didn't need, but the rest of the code needs. So at the end of each loop, we're going to put the environment back the way it should be, and then we're also going to, whenever one of these guards fail, put the environment back. So if we execute this code, what we see is our trace, and this is the optimized trace. So this last part here is the generated assignments that put our environment back the way it was supposed to be. And then when we say guard true, we say, oh, by the way, x3 is 11, x2 is 10, and x is 5. Our actual code has been reduced to one subtraction and a greater or equal to comparison here. So we subtract 11 from I each time and check to see if I is 0. At the top here, we say guard that x is 5, and there's nothing to update because we haven't created x3, x2, or x. So this part here of, oops, our guard fails, now we need to get the environment back to the way it was, is normally one of the most complex parts of a tracing JIT, and maybe even of any type of JIT. It's not bad in this case when you just have a hash map to update. But when you start to look at like modifying arrays or mutating objects or things of that nature, you may even have to go and create objects when the guard fails. In a real language, you may even have things like call frames and stuff to recreate. It's interesting to note that PyPy, in the Python language, at any time, you could actually dive into the function that you're currently executing and say, get me all of the variables that are declared up to this point in this function. That sort of introspection into the function is part of the Python spec. But PyPy has completely maybe removed all of that data down to just some registers. Your variables could just be registers. So what PyPy will actually do is when you say, hey, get me all the variables for this stack frame, it will actually bomb out of the trace, recreate all that information on the fly, and hand that object to you. So it's very fast if you don't touch the highly dynamic parts. And that's kind of what you look for when writing a JIT, is we're going to make the common path fast, and the not so common path that we still have to support, we're not going to worry about how fast that's going to be. So, all right. Now, let's go to our little bit more interesting example. Because the code we've been executing so far is very simple. So, let's go to our meta interpreter. Meta interpreter? Really? Yes. So, note this code is highly buggy. The one example we will look at today works. I cannot make a guarantee as to anything else. All right. So, to start with, we are going to define our new virtual machine bytecodes. We have an assign, we have a binary operation that assigns to a var the result of doing a operation of two other args. We have an inth and setinth, which will work with either strings or arrays. Setinth won't work for strings, but nth will work for both. And we have a jump. We have an if clause that if a variable is true, we'll jump to the then block, otherwise to the else block. We have a promote, and then we have guard true, false, and value. Today, we are going to first compile an interpreter for the BF language into this bytecode. And then we are going to interpret our interpreter and trace our interpreter, optimize the interpreter, and run the trace. We talked about before the problem of getting everything back to the way it was. And this is the cool thing that was developed by, this was the point of one of the papers developed by the PyPy developers, was the idea of writing JITs is hard. So let's write an interpreter in an interpreted language and then have a program analyze that interpreter and generate a JIT for you. And this process, as we call, is meta interpreting. So here's our interpreter. What we're going to do is ignore these for now. And then we're going to say we have code, a data, and stack. Now, these will be supplied to us from outside. These will be part of the environment that is handed to us by the interpreter interpreting this code. This may look like Clojure code. It is not. It is a reduced subset of, it's kind of a Lisp, but we don't have functions. We don't have anything else like that. It's just a way for me to easily write code this complex. So we have an instruction pointer, a data pointer, and a stack pointer. If the instruction pointer is less than the length of the code, this is also a constant handed to us, then we're going to get the instruction from the code. We're going to calculate this constant called IP plus 1. And then we're going to do a case on instruction. If it's a right angle bracket, then we increment our data pointer. If it goes the other way, we're going to decrement our data pointer. And each time we're using IP plus 1 to jump to the next instruction. Then we're going to, if it's plus, we're going to set inth in data, where the data pointer is. We're going to basically get the value at the data pointer, increment it by 1, and put it back into the data, and then go to the next instruction. The inverse for this, we can print char, get char of the current data at the data pointer. And then we have this fun stuff here. The first one says, if we have this bracket, that's the left angle bracket or the right? I guess it's the left. It comes on the left. We are going to increment our stack pointer and set the stack pointer to the current instruction pointer. And then we're going to recur to the next instruction. If we get a bracket going the other way, then what we're going to do is check the value at our data pointer. If the value of the data pointer is 0, then we're going to get our stack pointer -1 and go to the next instruction. So this is the loop is terminated, so we're going to decrement our stack pointer because we don't need that stack element anymore and continue. Otherwise, the stack pointer contains this instruction pointer we put in, and we're going to recur back to that instruction. So we're going to reset our instruction pointer to what's on the stack. Simple enough. So if we run this here, so first of all, we have a compiler for this wonderful language. So don't worry about all this. This is basically just a standard walking through and creating blocks for everything. And that's all of this code up to here. Let's restart a REPL because I have code. We're in the wrong namespace here. Okay. And pay no attention to all the code that's flying by. All right, good, excellent. So here's the code we're executing. It just prints out hello world. And we are going to go down here and look at some of our information. So analyze will take our interpreter and analyze it. And we will print line count of code. So when we're done, unable to resolve code in this context. Why are you unable to resolve code in this context? Okay, because we're not in the right namespace. How about that? All right, so let's get in the right namespace. Now, here we go. We have 26 blocks of code that we've created. And just for grins, if we do map count vals of code, that's how many instructions are in each one. And then if we do reduce plus, so we have 89 instructions. Our entire interpreter has been resolved down into 89 instructions, spread out over how many blocks? 26 blocks. So that's a lot of. I mean, for the interpreters and stuff we've been running, that's a lot of code. This is a pretty simple. This is not just a simple program. So now, if we run program, we get this output here. Now, here's a problem. Remember before, we said that we would trace something until we got to a certain number of, we've seen the same loop more than a certain amount of times. And then we're going to compile a trace of that. If we were to simply, on each one of these recurs, say, you know what, have we recurred back up to this part of the loop more than 2 or 3 times, now let's compile a trace, that would do absolutely nothing for us. Because what we would get, here's our dispatch. We would end up having a guard for this instruction, but it would change whenever the instruction changed. And so we would end up basically having a single trace for every single byte code in our hello world program. And then we'd have some giant switch statement switching in between all of these. And that is absolutely useless. We would spend more time jumping from one state to another than actually getting any work done. So instead what we're doing is we're introducing, and this is the key point of this meta-interpreting method, is we have this recur enter JIT instruction. And what this says is only start a trace when you get to this point in our interpreter, and only end the trace when you get back to this point in the interpreter. And by the way, when you create the trace, parameterize the trace with this recur point. So if this recur point changes, then you should be in a different trace. And this would allow us to have multiple loops in our code. So we see that here. This block 11 here says basically that's what this recur point is that we're going to the index, the instruction pointer of 11 for this trace. Okay, so that's kind of cool. So what does this look like? Well, let's output in our optimize here. Let's output the unoptimized trace, which looks like this. So when we run our program again, we get this. Now, this isn't even printing out all of the instructions, but we can see here, it says if the instruction pointer is less than the code length, then we're gonna guard that's true. And then we're going to get our instruction, or assign our instruction to the value of the code. So this is getting our current instruction out of that string. And then we're going to increment our instruction pointer and assign that to IP plus 1. And then we're going to guard value that the instruction is this right angle bracket. And then we're going to execute, this is the code for the first, for that instruction. Now what do we have here? IP is less than code length again. And again, down here, and again, further on. We see this over and over again. Well, that IP is less than code length is right here. So because we're only ending the trace when we see this again, what we've done is created a trace of all of the interpreter bytecodes from here to here. We have actually created a trace of our interpreter, not just of the bytecode in our interpreter program, but of the interpreter itself. So that's the first thing that we do to indicate to our tracing system that to enhance performance. We basically say, you know what, don't always create a new trace on every recur, but only when we say enter JIT. This is a good point to start a new trace, is what we're hinting. Now, down here, or up here at the top, it says optimize. Where is our other optimization? Did I comment that out? I probably did. Well, there's some stuff that we're printing out here. So let's remove that from that output from there, from optimize, and run this again. Now it says 535, we optimized, after we optimized this trace, we optimized 535 instructions down to 349 instructions. So this code here, from here to here, originally consisted of 535 instructions that have now been removed down to 349. But if we looked at those instructions, if you remember when we looked at those instructions before, we saw code length over and over and over again. Like, make sure it's less than code length, make sure it's less than code length. But the code length is a constant passed in to the system, and code is a constant. So we should be able to, and more than that, we know that when we start our trace, that recur point is going to enter, the recur point here is part of the parameters for the trace, because this is the instruction pointer. So the trace 11 here, so we know what IP is, so there's no reason to do this every time, right? We know the instruction pointer for this trace is always going to be 11. We know that 11 is always less than code, and then each time we add a value to the instruction pointer, we can continue to, every time we add a value to the instruction pointer, we can make sure that it's still less than code length. That should be able to be folded away. In addition, code is a constant, so there's no reason, because the constant is a string, we never change code, there's no reason to keep checking each one of these. So let's promote the instruction pointer. And the same thing for the stack pointer. Because the stack pointer is tied to this recur point value, we can promote that as well. All right, so now let's go look at our optimizer. So the optimizer looks a lot like the optimizer we just looked at a little bit ago. I have changed this up a little bit. This code is just a little bit cleaner than the code we've been looking at before. But what I wanted to look at was inth here. We were saying, after we resolved the to and from, or resolved the from and then the index, if our from is a string and the index is a constant, then we can constant fold the value from the string. Our strings are immutable, so we never have to update them at all. So the code we pass into this to be executed, the code meaning the code we pass to our BF interpreter, our BF code, is a string. Therefore, we can fold it, constant fold it away. So let's go up to our interpreter again, and this time we're going to output the result trace. Now what do we get after we've promoted those? It says 597 instructions have been reduced to 109 instructions. Now we have a single guard at the top. IP is 11. Stack pointer is 1. And all we have left is adding 1 to the data pointer, assigning that value back to the data pointer, getting the value out of our data at that data pointer, incrementing that value, and putting it back. Increment, 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 over and over and over and over and over again, until we get down here. And this is our check. So we get out of our data at the data pointer. We assign that to val. We say, does val equal 0? If not, then does val equal, if not, guard false. Yes, if not, then we continue. This always mixed me up that this is actually the inverse. It's not saying if it's false, go to here. It says if it's not false, go to here. Takes a little bit of thinking. Then we're going to set everything back up the way it was, and we loop again. And we can see here our hello world is printed out. And we'll print out these JIT keys, I call it, here at the end. So here at the end, we see if you are executing the code and you get to that recur to JIT point at this block, and the greens, as we call it here, this value that's right here in the recur, this recur point is 11, then you can go and execute this trace instead of jumping to that block. So there's a lot of code here. I've uploaded it. It's in a different file, but in the same GitHub repo as the rest of this code. But this is exactly what the PyPy project does, pretty much, is that you are writing in Python. So you write an interpreter in a reduced set of Python, just like this is kind of a reduced set of Lisp. That code you write is obviously compiled to Python bytecode. And then the PyPy toolchain analyzes your code and builds 3 different interpreters. The first interpreter it builds is a normal interpreter. It just takes this code right here, translates it to C, compiles it, boom, you're done. Secondly, what it does is builds a tracing interpreter, which is exactly like this code, but with the tracer. In fact, I'm not sure, but it may actually use a tracer interpreter. I'm not sure if it compiles your code to C with trace stuff in it, or if it actually runs it through an interpreter. I'm not sure about that. And then what it does on top of that is implements a third interpreter called the black hole interpreter, which is a really cool name, if nothing else. And what that does is when the guards fail, it kicks into the black hole interpreter, and that black hole interpreter is a very, very slow interpreter, but all it does is run enough of your code in this slow, like emulating the actual bytecode you wrote it in to get you back into the state that the environment that you expected. So when we had those guards with the variables in them all the time, that said, okay, when you're done, you need to merge this into the environment. Instead of having that just like one function, there's an actual interpreter that jumps to a part in your bytecode and starts executing to return everything back the way it should be. So that's pretty much what I have today for this. I mean, it's cool to go through this exercise of building all this out. We could obviously improve this a lot by, for instance, taking this trace and converting it into a closure code so that the JVM could optimize it to machine code. But, that could be an exercise for the reader. That's fine. I do have a bug as well where nested loops don't seem to work right in this, and there's no technical reason why they don't. I just don't want to spend any more time debugging it at this point. So there we go. I will link at the bottom of this video some papers talking about how this works, how meta interpreters work, and just how the PyPy project works in general. It's really cool stuff. I love studying it. Yes, once again, thanks for watching.